Here is a question number 245 from the Irodov from mechanics of rigid body or mechanics of solid body. In this question, it is given that a thin horizontal rod AB of mass m and length L can rotate freely about a vertical axis, passing through its end A. At a certain moment, the end B starts experiencing a constant force F, which is always perpendicular to the original position of the stationary rod and directed in the horizontal plane. Find the angular velocity of the rod as a function of the rotation angle phi counted relative to the initial position. So this is the diagram of the flowing problem. In this diagram, we are seeing that this is a rod AB whose length is L and which is rotating through an axis which is passing through an angular velocity omega, and there is a force F which is acting perpendicular to the point B of the rod. Now after some time, the position of the rod will be this position, which makes an angle theta with its original initial position. Now from this figure we can say that if this is the length L, so this length will be L cos theta. Now we'll write the torque equation. From the torque equation, we know torque equation will be I means moment of inertia into angular acceleration will be equal to force F into R perpendicular. So now this R perpendicular is nothing but perpendicular distance from the force F. So this is the perpendicular distance. The perpendicular distance is L cos theta. So instead of R perpendicular, we can write this is L cos theta. So we can write this again equal to F L cos theta. Now the moment of inertia for the rod when axis is passing through its one end is equal to m L square divided by 3, where m is the mass of the rod and L is the length of the rod, times alpha will be equal to FL cos theta. So now we can cancel L and square from this term. So after that we can find alpha will be equal to 3F cos theta divided by ml. Now as we know, alpha is nothing but rate of change of angular velocity. So instead of alpha we can put alpha equal to d omega with respect to dt. So d omega with respect to dt will be equal to 3f cos alpha cos theta divided by ml. Now this d omega with respect to dt further can be replaced by d omega with respect to d theta and d theta with respect to dt. That will be equal to 3f cos theta divided by ml. Now as we know, this d theta with respect to dt is nothing but angular rate of change of angle. It means angular velocity omega. So again we can write omega d omega with respect to d theta will be equal to 3f cos theta divided by ml. Now we will cross multiply this term. If we cross multiply this term, then we will get omega d omega, that will be equal to 3f cos theta divided by ml into d theta. Now we have to integrate this term both side. If we integrate this term both side, then our limit of integration for left hand side will be 0 to omega, and limit of integration in the right hand side will be 0 to theta. So from this equation, if we calculate the values, so integration of omega d omega will be omega square divided by 2, and its limit is from 0 to omega, and integration on the right hand side here, as we know, 3f divided by ml is constant. So first we can write 3f divided by ml. This is the constant term, and integration of cos theta d theta is equal to sin theta, and its limit of theta is from 0 to theta. So from this equation we can write omega square divided by 2 minus 0, that is nothing but omega square divided by 2, which is equal to 3f sin theta, which is equal to 3f sin theta divided by ml. Now we can further cross multiply this term, so omega square will be equal to 6f sin theta divided by ml. So if we want to find the angular velocity, then we have to square root of this equation in both sides. So our omega, or angular velocity, will be under root 6f sin theta divided by ml. So this is a short or required angular velocity of the rod as a function of theta.